Welcome to this lecture titled Technologies Enabling Artificial Intelligence. In this lecture, we will look at the technologies that make modern AI systems possible. Rather than treating AI as one single technology, we will examine it as a combination of different approaches, such as machine learning, natural language processing, expert systems, neural networks, robotics, and automation. The goal is to understand how these technologies contribute to AI systems that can interpret data, learn from experience, make decisions, and act in changing environments. This gives us a foundation for discussing both what AI can do today and where its current limitations remain. A key point is that AI is not one single technology. Instead, AI systems are built from several enabling technologies that work together. Some technologies help systems learn from data, others support language understanding, reasoning, perception, automation, or action in the physical world. In this lecture, we will look at technologies such as machine learning, natural language processing, expert systems, neural networks, deep learning, robotics, and robotic process automation. We will also connect these technologies to broader AI areas, such as decision making, problem solving, prediction, computer vision, and autonomous behavior. The purpose is to build a clearer picture of how AI systems are made possible, what different technologies contribute, and how they can be combined in practical applications. Artificial intelligence is enabled by several key technologies that work together to simulate aspects of human intelligence. These include machine learning, which allows systems to learn from data and improve over time without being explicitly programmed; natural language processing, which enables machines to understand and interpret human language; rule-based expert systems, which use predefined rules to make decisions; neural networks, which are computing systems inspired by the human brain and are capable of pattern recognition; deep learning, a subset of machine learning that uses complex neural networks to analyze large amounts of data; physical robots, which interact with the physical world; and robotic process automation, which automates repetitive tasks typically performed by humans. Together, these technologies can be understood as an artificial intelligence toolkit. Different AI systems use different parts of this toolkit depending on the task. For example, one system may rely mainly on machine learning and neural networks, while another may combine rules, language processing, and automation. Through these tools, AI can interpret external data correctly, learn from this data, and adapt flexibly to new situations, making it capable of performing tasks that typically require human intelligence. AI terminology requires some explanation because definitions in the literature are often vague and vary widely. Roughly speaking, AI can show behavior that appears similar to human thinking, for example, when systems support decision-making or carry out conversations. At the same time, not all AI capabilities are human-like in an obvious way. Some systems are powerful because they can detect patterns or deviations in large data sets faster and more systematically than a human could. In a broader perspective, AI can be found in computer systems that carry out tasks suitable for AI techniques. Advances in AI have also created the possibility of more automatic, self-managing, and self-repairing systems. However, creating computer systems that are smarter than humans in practically every field, including scientific creativity, general wisdom, and social skills, remains elusive. It is still not known whether this is even possible to achieve. Finally, many ordinary users do not always recognize when AI techniques are being used. We can describe AI from two related perspectives. The first perspective is AI enabling technologies. These are the tools, methods, and technical approaches used to build AI systems. Examples include machine learning, neural networks, natural language processing, expert systems, robotics, and robotic process automation. The second perspective is AI areas. These describe the kinds of tasks or capabilities that AI systems are used for. Examples include decision making, problem solving, language handling, learning, image processing, prediction, and cognition. These two perspectives can overlap. For example, natural language processing can be seen both as a technology used in AI systems and as an area focused on language-related tasks. The distinction is still useful because it helps us separate how AI systems are built from what kinds of tasks they are meant to perform. So, in the rest of the lecture, we will move between these two perspectives: the technologies that enable AI and the areas of activity where AI is applied. These technologies represent different ways of building AI systems. Machine learning is one of the most central technologies in modern AI. Instead of programming every decision manually, the system learns patterns from data. For example, it can learn to recognize spam emails, recommend products, detect fraud, or make predictions. Neural networks are one type of machine learning model. They are inspired by connected processing units and are often used for pattern recognition. Deep learning uses neural networks with many layers. This makes deep learning especially useful for complex tasks involving images, speech, language, and large data sets. Natural language processing focuses on human language. It allows AI systems to classify text, translate between languages, summarize information, generate text, or respond to questions. Expert systems work in a different way. They use rules created by humans, often in the form of if-then logic. This means they do not learn from large data sets in the same way as machine learning systems. Instead, they apply predefined knowledge to support decisions in a specific area. So, this slide gives us a simple distinction. Some AI systems learn from data, some process language, and some reason through explicit rules. In practice, these approaches are often combined. One important AI area is multi-agent and agent-based systems. These systems can perform tasks either individually or together as teams with more or less intelligent behavior. The key feature is the separation of the environment in which the agent operates from the mechanisms that make up the agent. The simplest form is a software agent that may perform a single task, while advanced intelligent agents can carry out complex tasks together in multi-agent systems. Examples include searching data on the internet and self-driving cars. Agent-based systems can also interact with the stock market with single agents that buy or sell. They can also negotiate prices and participate in auctions and bids. The impact of these software agents in the stock market can be far-reaching and serious. Robotics is closely related to computer vision because many robots need some way to perceive and interpret their surroundings. For example, a mobile robot may use cameras or sensors to detect objects, avoid obstacles, and navigate through an environment. In this lecture, we treat robotics and computer vision as related but separate AI areas. Robotics focuses on systems that act in the physical world, while computer vision focuses on interpreting visual information such as images and video. Robotics is interdisciplinary. It combines mechanical engineering, electrical engineering, and computer science. Not all robots are highly intelligent. Some follow simple, predefined rules, while others are more autonomous and can adapt to their surroundings. Examples include soccer robots such as NAO, human-like robots such as Sophia, and mobile autonomous robots that move through physical environments. Robotic process automation is different. Despite the word robotic, it does not usually refer to physical robots. Instead, it refers to software that automates repetitive digital tasks, often by mimicking actions that a human user would normally perform in software systems. Robotics is commonly tightly linked to computer vision. However, computer vision is described here as its own AI area. Vision involves capturing images and videos and interpreting the contents to gain understanding and detect events. It is a part of perception, which seeks to interpret and combine senses to gain understanding, and virtual reality or augmented reality illustrate how reality can be altered. For example, in augmented and mixed reality, computer vision can help systems recognize surfaces, track movement, and place digital objects in relation to the physical environment. The thread weaving through this lecture is that AI rests on a suite of enabling technologies that together let machines interpret data, learn from it, and act in ways that resemble intelligent behavior. We begin with learning and interpretation. Machine learning and its deep learning subset provide the means to extract patterns from data, while natural language processing gives machines access to human language. Rule-based expert systems remind us that not all intelligence must be learned from data. Predefined rules still guide many decisions. Neural networks, especially in deeper forms, are central to pattern recognition across diverse domains, and they sit alongside physical robots and robotic process automation, which extend intelligence from abstract data to real-world action and to automated, repetitive workflow tasks. Beyond tools, the discussion maps AI onto areas defined by tasks: deciding, solving, language handling, learning, behaving, processing images, predicting, and cognition, showing how different capabilities cluster and how they can combine in practice. Multi-agent and agent-based systems illustrate intelligence that emerges from many interacting agents operating in shared or separate environments, from internet data searches to self-driving cars and even stock market negotiations. Robotics and computer vision occupy adjacent, overlapping spaces. Robotics focuses on physical systems, while robotic process automation refers to software-based automation, and computer vision is treated as its own broad area, with perception serving as a unifying aim to interpret sensory data. Perception, in turn, links to broader notions of reality manipulation seen in VR and AR, underscoring how AI systems interpret and sometimes alter our experiences. An overarching point is the ongoing move toward more autonomous, self-managing, and self-repairing capacities, even as the aspiration for universal, human-level intelligence remains elusive. The takeaway is that AI is not a monolith but a tapestry of interlocking technologies and domains, each addressing distinct tasks while sharing substrates like perception, learning, and action. This framing helps us assess capabilities, recognize limitations, and anticipate how AI will continue to integrate into real-world problems.